Hello, Doctor. I am Lin Garlok from Session 1, Home Group 5. Today we will present about the filtering process. First, we load the audio signal into MATLAB using audio read function. This function can read the waveform data along with its sampling rate. The name of audio file is s1g5.wav. Next, we normalize the signal. We divide the entire audio waveform by its maximum absolute value and scale it into the range of -1 to 1. This process is to prevent numerical issues or creeping, especially during filtering. The next step is to design a bandpass filter to isolate the frequencies that are most important for human speech. We focus on the range from 100 Hz to 4 kHz. This range captures most of the speech energy. We design a 10-order IRR bandpass filter which provides a steep roll-off to reject noise outside speech band. There are the cost functions are used to design filter. First is to design an IRR filter. Second is to determine the order of the filter. Third is to set bandpass edge. And last is sampling rate of the signal. Finally, we apply the bandpass filter to the normalized signal. This step remove low frequency noise which below 100 Hz and remove high frequency noise which above 4 kHz. After these steps, the signal contains mostly speech and less background interference.
Hello doctor, my name is Havesh Anlaki Ravi. Before analyzing the signal frequency domain, we first configure the short time Fourier transform, also known as STFT parameters. We choose a Hamming window with a size of 256 samples, which helps reduce spectral leakage. To improve time resolution, we apply a 50% overlap, which in this case is 128 samples. We also set the FFT, which is fast Fourier transform length, to 512, allowing for detailed frequency analysis. These settings together balance both time and frequency resolution and prepare the signal for STFT computation. Next, we compute the STFT using MATLAB's STFT function, which transforms the signal into a time frequency spectrogram. We input the configured parameters like the signal, sampling rate, window, overlap, and FFT length. Then, to estimate the noise profile, we assume the first 0.1 seconds of the signal is silence. By averaging the magnitude of those initial frames, we create a baseline noise spectrum which can later help in noise reduction or speech detection process. Just like the MATLAB code above here. Thank you.
Hi, my name is Liu Zhonghan, and I will be explaining about the aggressive spectral subtraction part. First, we use ABS spectrogram data to give the magnitude spectrum of the noisy signal. And then we have 2.0 multiplied with noise magnitude profile, which aggressively estimates and subtracts twice the average noise spectrum. And then we use max process magnitude 0 to ensure that there's no negative magnitude remains. And next we have the weak frame suppression part. In this part, the energy is calculated per frame to determine how strong the signal is in each time window, and a dynamic threshold is set to 10% of the max frame energy. Any frames below the threshold are considered silence and zeroed out in the magnitude spectrogram. For the reconstructing part, the original phase of the spectrogram is kept and combined with the news magnitude to form the noise spectrogram.
Okay, my name is Javier. So I'm presenting the inverse STFT and post-processing. After denoising the spectrogram, we use inverse STFT to convert it back into a time domain audio signal. This step reconstruct the waveform by using the same windows, overlap and FFT settings from the original STFT, ensuring accurate time and frequency alignment. Next, we apply a post-processing to clean and enhance the output. First, we remove the small imaginary values that can appear due to numerical roundings. Then we normalize the waveform so its peaks stay with the -0.1 range, preventing any distortion. To improve the clarity and make the audio louder, we apply a slight gain boost. Finally, we set the enhanced audio as a new WAV file ready to playback for further use.
My name is Ku Xing and I'd like to present the last part, which is how to save the output. So the first, we need to give a definition for the file name. And for the file name, we just name it like what we like, and we just create a string variable. And for next, we will doing audio writing, which used to set the processing signal as in 16-bit WAV file and the code that we use is audio write, and we giving the output file name and the reconstruct signal and the sampling rate, and the reconstruct signal and sampling rate actually we get from the previous. And for last is about the user confirmation, which we write the fprint to give the information to us to know that actually the code already run and successful. So for next, I will to present the way that I run the code. So here's our input file, and we already give it a location to the this audio read, and here's our file, our code file, and here's our output file. When we run it, and it will give us the file like this, name like this. So we run it, and it says that it is saved. And here is our new output file. So that's all. Thank you.